Okay, so we've got the eigenvalue problem. And the eigenvalue problem just basically says if you multiply a vector by a matrix, as you've done, and you look at how the unit circle deforms into an ellipse and so forth, and how the vectors around the unit circle deform, some of them get further apart, some of them get closer together. We ask what vector, after you multiply it by the matrix, after you transform it, ends up along the same straight line. Okay? Now, it's not necessary that any vector does. Like, you could just rotate the whole circle and nothing would be along the same straight line where it started. Every vector would be pointing in a direction different. Okay, so rotations don't have eigenvectors. Okay? However, the same dimensional matrices do. Okay? So this might be a little bit familiar. So we take a bunch of vectors around the unit circle and we multiply them, let's just say by the same dimensional matrix or by any other matrix. And let's just say that what you end up with, okay, the vectors themselves are the white ones, and these three vectors here give you these three vectors. Okay? And I don't like the way I drew that picture. It's kind of big. Because obviously this vector and this vector end up in the same direction, right? And it turns out that no other vector will. In two dimensions, at most two vectors end up in the same direction they started. Okay?
Real quick, I wanted to apologize because second piece of homework, but I got your email last night after, I didn't know I was going to have to work yesterday, but I did, so.
Get it for Thursday.
All right.
Yeah, I still don't know why that assignments page is pointing to the pre-calculus, except that probably I screwed up. So I got to fix it.
Could it probably be the engine of the browser?
No, I wrote the thing. It's me. Okay? Okay, so again. And what I'm drawing here is kind of a typical thing that happens with the same dimension and allows us to use the idea of eigenvectors. And incidentally, what we're doing today doesn't depend on what we did last time anyway, but it was fairly straightforward, just some matrix reductions to be able to do it easily. Okay, so let's just say we take these vectors around what's supposed to be a circle that kind of screwed up, okay? Now, when I transform this vector, it goes here. When I transform this vector, it goes here. When I transform this vector, it goes here. Okay? Can we conclude that there's a vector between these two that has to go to itself? Well, geometrically, this one turns this far, this one gets turned this far. This one gets turned a little further than this one, maybe, okay? So I'm thinking that if we transform a vector about here, transform vector might be in the same direction. Whether that makes sense to you visually or not, don't worry about it. I want to establish, I mean, if it does, that's great. But I didn't draw this as clearly as I'd like, but I want to establish the idea that we're looking for vectors that go to vectors in the same direction. Okay? Or at least along the same line. It could be that some of the vectors, like this vector, goes to vector in that line. Okay, that would still satisfy. Well, anyhow, let's look at the question of whether the same dimensioned matrix,
A colored marker. Or a pen.
Option of thing.
whether the same dimensioned matrix transforms any vector in the direction of itself. Okay? So, let's just take the 0.9, 0.2, 0.1, 0.8, the basic same dimensioned matrix, and say that that matrix multiplies the vector x, y, and gives you some multiple of x, y, some number times itself. Okay? And I'm going to call that number the Greek letter lambda.
How do you spell that word?
Lambda. Okay? Now there's something I can do with matrix algebra, but we haven't done a lot of matrix algebra, so I'll probably do it too. But we see that this represents a system of equations. Okay? And actually, I kind of want to do the matrix algebra. Okay? So I'm going to change my notation a little bit. I'm going to call this just A, B, and this is A, B. Okay? Now I'm going to call this matrix A. We're going to call this AB vector X. So the equation becomes AX equals lambda X. Okay? And we want to solve this. And at least we want to find if there's a lambda that makes this true. Okay? Now I could rewrite this in terms of simultaneous equations and do the whole thing. But I've just decided I want to use this to establish a little matrix algebra. Okay? So I'm going to digress. I, this matrix, that I times x equals x for any x, for all x. That upside down A means for all. Notation that you should have seen at some point, but maybe not recently. Okay? So I want to be sure to explain it. Okay? Proof. Very simple proof. This can be any x, any vector. A can be anything, B can be anything, any real number, okay? Or complex number if you want. Then Ix is this, and you can verify it. If I multiply this matrix by AB, I get AB. So pretty much a no-brainer. You just write it out. A lot of proofs are like that. Most of them aren't quite as simple as this, but sometimes you just got to write it out. I want to prove that matrix A, B, C, D multiplied by the matrix E, F, G, H is different if I reverse the order. I've just got to write out what I get from this one and what I get from this one and show that they're not necessarily the same. It's a matter of writing it out, then finding values of A, B, C, D, E, F, G, H that make them different, okay? Or I could just make up a simple matrix, okay? 1, 2, 3, 4 times 3, 4, 2, 1. That might not be a good idea. Yeah, and show that there is at least one matrix where it doesn't work. Okay? So that's kind of the idea of proof. You got to write down a series of statements that can't be refuted, that cover all bases, and establish what it is you want to establish. Okay, well, that's the identity matrix. Okay? And also, if you multiply the identity matrix by any matrix A that's compatible for multiplication, because of course the columns of A have to match the rows, length of the rows of I, and to do it in the opposite direction, the same has to be true. So they both have to be square matrices. Okay. Anyhow, you establish this. That's very much like the role of the number 1 in basic arithmetic of real numbers. 1 is the identity. Okay? Now there's much more that I can say, but having established this, I can come back and do something here. This is equivalent to saying that AX equals lambda I times X. Since X is just equal to IX. Okay? And I got to put the parentheses here. Now, we haven't proven it, but another thing is, the operation of matrix multiplication is associative. And that's something you can easily do if you got a little matrix notation, a little notation for the elements, just by writing it out. Even for a 2 by 2 matrix, it's a mess, and when you do it for general matrix, it's a bigger mess. But it's an easy mess, as long as you can handle messes. Okay? So you're going to accept this for now. Okay? The matrix multiplication, there's an algebra of matrix multiplication. It has rules just like the algebra of real numbers, or complex numbers. Okay? And this is one of them. There's an identity. Okay? There aren't necessarily inverses. Okay? And there is associativity, but you don't have commutativity. Okay? So there's several properties of matrix multiplication. Most of them are obvious, and the ones that aren't obvious you can easily believe just by writing a couple of matrices down and doing an operation. Okay? And we're going to develop all that. Right now we're skipping way ahead to eigenvectors and eigenvalues, so we can talk more about the same dimension problem. So now, I can say that because of the fact that matrix multiplication is associative, and also there's stuff about multiplication by constants that acts exactly the way you'd expect it to. We can prove that you have properties that allow us to write this. We'll just change the grouping here. Now, we haven't really, matrix, associativity of matrix multiplication doesn't quite get it because lambda isn't a matrix, just a number. Okay, but it's even easier to prove for numbers. That kind of associativity works. And we will be proving those properties once we get the text next week, hopefully. Okay? But I want to show you how this stuff works and how neat it can be, rather than working through a bunch of examples that are fairly neat themselves. We're going to do something really neat. Okay? So, we have this. That's equivalent then. And I've got to put an arrow over that 0 because this is a vector and this is a vector, and they've got to add up to a vector, right? I mean, whatever's here has to have two components, okay? And distributive law works. Again, easily proven. So we can use the distributive law here and say that A minus lambda I x equals the 0 vector. Well, okay. And because A minus lambda I is this. I'm going to write that out. And instead of x, now I'm going to write our AB here. Okay? Now over to the right here, I'm going to write okay. If I multiply a number by a matrix, then I multiply it by every element in the matrix, every entry, every number, and every row, and every column. That's what it means to multiply a matrix by a number. And then if I add two matrices, I just add them element by element. So I get 0.9 minus lambda 0.2 minus 0. Okay? 0.1 minus 0. 0.8 minus lambda, which is just this matrix. Okay? They've got established properties, but all these things look like they ought to be about right. And it's easy to prove that they are, once we get the book in our hand. Do a little more with that. Okay? So I'm going to take this up here and say that, okay, I would think ahead about what I'm writing. Maybe I wouldn't do this. Maybe in some universe somewhere I'm doing it right. But, okay. There a little bit. Okay, well, this product is 0.9 minus lambda times A plus 0.2B. And then the other one is 0.1A plus 0.8 minus lambda B equals 0. Okay? Well, we go back to the simultaneous equations because that's the basic thing that we understand. Okay? When in doubt, take things back to the simultaneous equation. Now, if you got two simultaneous equations in A and B, you know that you can solve them using row reduction. Okay? Now, if we had more machinery, if we'd done determinants, there's a really easy way to do this. But what we're doing is equivalent to it, and when we see it later, I'll bring it back to the analogy here so you kind of understand the whole thing a little more deeply. It's not just magic. Well, there's a perfectly good system of equations written as a matrix that we can easily reduce. Okay? So how would you want to reduce this? Well, keep that visible, but I could do this, and then I could multiply the first row by 10 and get 1 here, okay? And 0.9 minus lambda and 0.2 is 0. Then I could take 0.9 minus lambda times the first row, subtract it from the second row. Or negative 0.9 minus lambda plus the first row, subtract from the second row. You get a 0 here. Okay? When I do that, then what I'm going to do is I'm going to have the 0.2 minus 0.9 minus lambda times this, right? So I'm going to write that down over here because it's kind of cumbersome. Okay? And I'm going to expand this. So 0.9 times 8 is 7.2, right? And then 0.9 times 10 lambda is 9 lambda, and you got 8 lambda, so you got minus 17 lambda. Then you got plus 10 lambda squared, which is 10 lambda squared minus 17 lambda minus 7. Okay? So I'll write that here. And then I still got 0.
I'm still at that step right here. Like I didn't get to write it down
Well,
while you're.
you know, don't worry too much about writing it down as I do it, but think about what I'm saying, okay? Because I'm going to post the pictures, like apparently they haven't been posted. But yeah, y'all been, what you did last week looked really good, and I don't think it's going to disadvantage you. I don't think you needed it last week. This week you might need it because you might need my words, okay? So try to absorb as many of my words as you can. Not that they're necessarily great words, but it's the best you got right now, so live with it. Okay, now, well, what do you see about this matrix? That's what we really want to focus on right now, because everything else is just straightforward mechanical process. And if you haven't yet done the matrix reductions, once you do, you're not going to have any trouble with the process. What's the second line say? How does that translate to an equation?
Expression is equal to 0.
Yeah. It says this has to be 0 because if this is going to be a valid reduction, it's your only choice. Okay, so second line requires that 10 lambda squared minus 17 lambda minus 7 equals 0. Okay? So how do you solve that? What kind of equation is that?
Quadratic.
Quadratic equation. What are your options for solving a quadratic equation? Well, the option you're generally going to come down to is the quadratic formula, simply because you rarely find something that factors, although this does. Okay? So you would ordinarily use a quadratic formula, and when I have you do the same thing with your matrix, with the A, B, C, and D and stuff that you used before, because you're familiar with that matrix, okay? And you're familiar with the way it works. Get factors like this: 10 lambda minus something, lambda minus something. And this is going to be minus 7, and this is going to be minus 1. Because that gives you negative 10 lambda and negative 7 lambda, which is negative 17 lambda. But when you get to your matrices, it's not going to be as nice. I don't think you're going to get anything that you can easily factor. Okay? This one's fairly easy. Actually, you will. but you might not recognize it. So if lambda is 1, it works. If lambda equals 0.7, it works. So let's say lambda 1 equals 1, lambda 2 equals 0.7. Okay? And these are called my eigenvalues. Call them eigenvalues of the original matrix, or original single-dimensional matrix. Okay? Having the eigenvalues, it now becomes easy to find the eigenvectors. Okay? So now, I don't have the matrix written down anywhere here. Okay, so I'm going to have to write it down again. 0.9 minus lambda, 0.2, 0.1, 0.8 minus lambda, is equal times the AB vector equals the AB vector. That's where we started. And we found that that can be true if lambda 1 equals, if lambda is 1 or if lambda is 2. Okay? And I said equals AB. And I can't use lack of sleep as an excuse. I was sleeping fairly well. Can't use pollen as an excuse as I usually can because it's not bothering me particularly. It's just plain old inattentiveness. And clearly this is supposed to be the 0, 0 vector.